Hello. Today we're going to talk about properties of logarithms. So one of the properties I want to talk about today is called the product property of logarithms. So what the product property of logarithms says is that if you have a logarithm with two values being multiplied together, that you could separate it and write it as two separate logs that are being added together. Or if you have two separate logs being added together, you can combine them into just one log, multiplying those two answer spots together. Now, why does this work? Because logs are dealing with exponents. And so when we remembered that if I had 2 raised to the third power and I multiply times the same base, that was essentially a 2 raised to the 3 plus 1. So even though the bases were being multiplied together, in the exponents I'm adding them. And logs are dealing with exponents. So what exponent goes on 2 to make that answer? Okay, so let's look at this in logarithmic form. If I have log base 2 of 8 times 2, we know that's really just log base 2 of 16. So if I have log base 2 of 16, then I'm asking what exponent goes on 2 to get me a 16. And we know that the exponent that goes on 2 to get a 16, this whole thing simplifies down to be just a 4. Okay, well then, if I have log base 2 of 8, what exponent goes on 2 to make an 8? We know that that's a 3. And of course, what exponent goes on a 2 to make a 2? Well, it's not really increasing much. It's just a 1. Now notice that 4 does equal 3 plus 1. And so that's why it works, because we're adding our exponents when the bases are multiplied together. So these are like two bases being multiplied together. Now if that works for adding and multiplication, then the same thing has to be true with subtracting and division. So if you have a log base 2 of 8 divided by 2, we know that's really just log base 2 of 4. That's going to equal the same thing as log base 2 of 8 minus log base 2 of 2. We know what exponent goes on 2 to get a 4. That's just a 2. A 2 squared makes 4. And what exponent goes on 2 to make an 8? Well, we know that that's a 3. And minus the log base 2 to get a 2 is just a 1. And notice 2 does equal 3 minus 1. The third one we're going to talk about today is the power property of logarithms. And this one's interesting, because if I have an answer that has an exponent, they're saying that I can take this 3 and move it out front and go 3 times that log of just the 4. Okay, let's check this out and see if this works. We know what 4 cubed is. 4 cubed is 64. So log base 2 of 64, does it equal 3 times the log base 2 of 4? Well, how many 2's does it take to get to 64? What exponent goes on 2 to get 64? We know that is 6. 6 2's. So 2 to the 6 equals 64. Then does 3 times, now what log base 2 of 4? What exponent goes on 2 to get 4? Well, 2 squared. So the exponent would be a 2. Now does 6 equal 3 times 2? Yes, it does. So that's kind of nice. And you might be thinking, well, what are some of the advantages of knowing these properties? Well, if you're going old school and you have a logarithmic table, you don't have fractions in that table. So you might have to take, if you're looking for a log base 3 of 2/3, how can I rewrite this? I can rewrite this as the log base 3 of 2, and because it's divided, subtract and say log base 3 of 3. Now, in my old table, I know that the log base 3 of 2 is 0.6310, and I also know that the log exponent on 3 to get a 3 is just a 1. So I can go and subtract these, and I can estimate the log of 3, log base 3 of 2/3 is about 0.369. So that's one way we can write these. But more applicable is using algebra. What if you have multiple logs? What if they're added or subtracted together? What if I still need to solve for n? Well, we had a property that says if I have a log of one thing equals the log of another, and they have the exact same base, I can just drop the log. But if there's a subtraction happening in there, then you cannot do that. So I have to combine these into the log of one thing equals the log of another, which means with this subtraction, I'm going to use that property to say the log base 3 of 42, and because it's subtraction, it's not going to be multiplied, it's going to be divide by n will equal that log base 3 of 7. Now that you have the log base 3 of 42n equals the log base 3 of 7, and there's nothing else, now you can drop your logs and call it just 42 over n will equal 7. And now you can solve it like normal. So being n's on the bottom, I'm going to have to times by n on both sides. N cancels an n, and I'm just left with a 42 equals 7n. And then divide by 7 to get n equals 6. And so I can still solve for variables by putting these together using these properties. Okay, sometimes there's multiplications, and we have to move that, because even though it looks like there's only 2 logs, there's still a multiplication of a 2 times a log, keeping me from being able to just drop the logs. So I got to move, using that power property, move that 2 back into the exponent spot, and this is going to look like the log base 5 of x squared will equal the log base 5 of 9. Now that this log base 5 equals a log base 5, you can drop those log base 5s, and x squared equals 9. And then simple solve, square root both sides, and you get x equals plus and minus 3. Okay, but wait a second. There's something we got to remember. This originally came from a log, and this x was in an answer spot. In other words, 5 raised to some exponent turned into that x. 5 raised to the 3rd power. But wait, can this ever become negative? How many 5 times 5 times 5 ever makes a negative value? It doesn't. And so in this situation, depending on where that x is, you're going to have to watch out, because you cannot have that negative there. You're going to have only x equals positive 3. So let's do another example. Okay, I have a couple logs together. They're all the same base. I see 2 logs, which you might want to just drop the logs, but notice it's not a log base 10 equals a log base 10. And you don't want to necessarily subtract them, but with this plus, you can combine them. So let's combine them first, and let's write this as a log base 10 of a. And then this plus here is going to change to a times, and then I can write a plus 21. Now all of that's going to still equal 2. But I only have one log. Log base 10 of one thing will equal 2. How do I solve that when there's only one log? You can't just drop it, but we can write it as an exponential. In other words, this 2 is an exponent, And so I can take this 10 and write it in exponential and call this an a times a plus 21 equals 10 squared. So there's my exponent. Then I can distribute and just solve for a. Now we get an a squared plus 21a equals 100. Now because of this x squared, I'm going to have to, it's a quadratic, I'm going to have to solve it like a quadratic. So let's get it equal to 0. Let's minus 100 to both sides. And we're going to get a squared plus 21a minus 100 equals 0. Does it factor? Let's try it. Well, a times a makes my a squared. I'm looking at 21 and 100. Factors of 100, something like maybe 25 times 4 makes 100, but it's negative. So one of them's plus, one of them's minus. Since I have a positive 21, I'm going to have the positive in the big number and the negative in the small number. Now I can solve these, and I say, well, then a has to equal either a negative 25 or a has to equal 4. But I got to look back to my original problem, because in my original problem, these answer spots cannot be negative. So a has to be greater than 0, or this whole thing has to be greater than 0. So if a is greater than 0, then 0 plus 21 is obviously going to be bigger than 0 no matter what. So this negative 25 is not bigger than 0. That means that can't be our solution. So our only solution is a equals 4. Hope that helps. Give it a shot. Good luck.